Welcome to this session regarding questions and answer in thermochemistry. Last time we ended question 15. Today we are starting on question 16. Question 16 is saying 100 grams of unknown metal at 150 degrees Celsius was dropped in a bucket containing 50 grams of water initially at 21 degrees Celsius. The final temperature of the mixture was 32 degrees Celsius. Then they're asking what the specific heat capacity of the metal, and the specific heat capacity of water was given as 4.184 joule per gram degree Celsius. Let's move to the answer. We have a metal with high temperature and a water with a low temperature with 21 degrees Celsius. That means there will be a flow from 150 degrees Celsius of unknown metal to the water with 21 degrees Celsius. That means that the metal will lose the heat while the water will gain the heat. The heat that is lost by the metal will be gained by the water. So that means that the heat for the metal will be negative, and for the water, the heat will be positive. Remember, the heat is equal to the mass times the specific heat capacity times the change in temperature. Q is negative when heat is lost, and positive when heat is gained. So this means that heat energy lost by metal is transferred to the water. So one is losing the heat, another one is gaining the heat. So the Q gained by the water will be positive, and the Q lost by the metal as conversion we put negative sign. Let's try to put in kind of the formula. We have the mass of the water times the specific heat capacity of the water times the change in temperature of the water, which will be equal to minus because the metal will lose the heat, mass minus mass of the metal times the specific heat capacity of the metal times the change in temperature for the metal. Then we have the mass. We have the mass and the specific heat capacity of the water and change in temperature. Then we can substitute the value. So we have 50 grams as the mass of the water times 4.184 joule per gram degree Celsius as the specific heat capacity of the water times the change in temperature, which will be 32 degrees Celsius, which is the final temperature, minus 21 degrees Celsius, which was initial temperature. This will be equal to 100 grams of the metal, but we need to put minus 100 grams of the metal times the specific heat capacity of the metal, that is unknown, that we need to calculate. Then at the change in temperature, it will be 32 degrees Celsius, which is initial the final temperature, minus 150 degrees Celsius, which is initial temperature. Final 32 degrees Celsius minus initial 150 degrees Celsius. If we can rearrange, we can multiply and also do a sum of the addition, then we will have to calculate the unknown, which is the heat specific heat capacity of the metal, and we will see that the C, which is specific heat capacity for the metal, is equal to 0.195 joule per gram degree Celsius. Let's move to next question, and the next question is question 17. Question 17 is saying 100 grams of aluminum at 120 degrees Celsius and 150 grams of iron at 90 degrees Celsius were placed in a container of 80 grams of water at 15 degrees Celsius. That means here we have aluminum, which is having 120 degrees Celsius, and the iron, which is having 90 degrees Celsius, and they were placed in water with 15 degrees Celsius. That means that we have the transfer of heat from the high object to the low object, or from the high temperature substance to the low temperature substance. That means that the heat will flow from aluminum to water, and also the heat will flow from iron to water. Now they are asking what is the final temperature of the mixture. They have given the specific heat capacity of the water which is 4.184 joule per gram degree Celsius. Specific heat capacity of aluminum was given as 0.9 joule per gram degree Celsius, and specific heat capacity of iron was given as 0.45 joule per gram degree Celsius. Let's see the answer. So we know that the heat will move from aluminium to water and from iron to water. That means that the heat lost by aluminium and the iron will be gained by the water. So the Q for the aluminium will be negative, the Q for iron will be negative, while the Q of water will be equal to positive. So that means that the heat lost by aluminium plus heat lost by the iron will be equal to the heat gained by the water. Aluminium will transfer the heat to the water, so the Q it will be a negative. Iron will also will also transfer heat to the water. The Q will be negative. So then water will receive heat from aluminium and from iron. So we get the water which has Q which is positive. Then that is the formula. The mass of the water, C water times dt, will be equal to that is the heat again by the water will be equal to the heat lost by the aluminium plus the heat lost by the iron. So remember, we are putting the negative sign because there is a loss of heat, and the positive sign here because there is a gain of heat. We can put the values. The mass of water was given as 8 grams. The specific heat capacity of water was given as 4.184 joule per gram degree Celsius. The TF minus 15 degrees Celsius. This is the initial temperature for the water. Then it will be equal to minus the mass of the 100 grams, the mass of aluminium, times the specific heat capacity of the aluminium. TF minus the initial temperature of the aluminium, then plus minus 150, which is a mass of the iron, times 0.45 joule per gram degree Celsius as the specific heat capacity of the iron, and then TF minus the initial temperature for the iron. So the unknown with that to have in the equation is the TF. Then if we can multiply and do some of the addition and the other rearrangement, then we can get the TF, and we will see that the TF is equal to 44.48 degrees Celsius. So the logic here is to know that the heat lost by the hot object will be equal to the heat gained by the less temperature object. Let's see the next question. The next question is the 18, the number 18. Question number 18. Question number 18 is saying you have an unknown metal of 300 grams at 200 degrees Celsius was placed in 50 grams of aluminum pot containing 100 grams of water at 21 degrees Celsius. That means that the pot and the water was having the same initial temperature, which is 21 degrees Celsius, while the unknown metal was having 200 degrees Celsius. The final temperature of the mixture was 29 degrees Celsius. Then they are asking what is the specific heat capacity of the unknown metal. Specific heat capacity of the water is given, is here. A specific heat capacity of aluminum is also given as 0.9 joule per gram degree Celsius. So let's go to the answer. So that means that there will be a flow of heat from 200 degrees Celsius unknown metal to aluminum pot, and also there will be a flow of heat from this metal, is unknown metal, to water. There will be a flow of heat to aluminum pot and a flow of heat to water. So that means that the heat lost by the unknown metal will be equal to heat gained by the aluminum pot and plus the heat gained by the water. Initially, the aluminum pot and water have the same temperature of 21 degrees Celsius. So the unknown metal will transfer the heat to the water and to the aluminum pot. So the Q will be positive for the water and for the aluminum pot. Then water will receive heat from an unknown metal. So Q is positive. So aluminum pot will also receive heat from an unknown metal. Q will be positive. Then let's now put the kind of formula. So that means that the mass for the metal, the specific heat capacity for the metal times the change in temperature for the metal will be equal to the mass of the pot times specific heat capacity of the pot times the change in temperature for the pot plus mass of the water times specific heat capacity for the water times the change in temperature for the pot. Then you can put the value and then sort and solve for the unknown, which is the specific heat capacity for the metal. So note that we have the final temperature is 29 minus 200 degrees Celsius for the initial temperature of the metal. Here also the final temperature is 29 minus the water was having the pot was having 21 degrees Celsius as initial temperature. The same as here, the water also, because it is in the pot, it was also having 21 degrees Celsius as the initial temperature. The pot and the water were having the same initial temperature, 21 degrees Celsius. If we can then multiply and we will put some terms on one side and the others on the other side, then we will do some mathematical calculation, then some rearrangement of the terms and some of the multiplication and the addition. Then we will get that the specific heat capacity of the metal will be equal to 0.0723 joule per gram degrees Celsius. Let's go to the next question. So which is question 19. Question 19 is saying we have 50 milliliters of water at 20 degrees Celsius was mixed with 100 milliliters of water at 90 degrees Celsius. Determine the final temperature of the mixture. If the density of water is 1 gram per ml, the specific heat capacity was given as 4.184 joule per gram degrees Celsius. Here we have two different water. One water is having 90 degrees Celsius, it's very hot. Another water is having 20 degrees Celsius, it's not hot. So that means there will be a flow of heat from water which is hot to the flow of heat to water which is having 20 degrees Celsius. So that means that the Q, the heat of the water with 90 degrees Celsius will be negative, while the water, the Q for the water with 20 degrees Celsius will be positive because we gain the heat. So 90 degrees Celsius, water will transfer heat to the water with 20 degrees Celsius. So that means that the mass of the water 20 degree times specific heat capacity for water 20 degree times the change in temperature for the water with 20 degree is equal to minus mass of water with 90 degrees Celsius, because this will reduce the heat. That's why we put negative. So times the C for the water with 90 degree times change in temperature for the water with 90 degrees. So if then we can see in the formula we don't have the mass of the water. Mass of water at 20 degrees Celsius and the mass of water with 90 degrees Celsius is not there. So we need to calculate the mass from the density. We know that density is equal to the mass dividing with the volume. So that means that the mass is equal to the density times the volume. Mass is equal to the density times the volume. Then that means mass of water with 20 degrees Celsius is equal to 1 gram over ml times 50 ml, you get 50 gram. And then the mass of water with 90 degrees Celsius will be equal to 1 gram per ml times 100 milliliter, then you get 100 gram. Here, after getting the mass, then we are going to use the formula by replacing the mass of the water at 20 degrees Celsius times the specific heat capacity of the water, Tf minus 20 degrees Celsius is equal to minus mass of the water at 90 degrees Celsius times 4.184 specific heat capacity of the water, Tf minus 90 degrees Celsius, which is the initial temperature for the water with 90 degrees. Here also the initial temperature is 20 degrees Celsius. So we need to calculate the final temperature, which is Tf. Then we can multiply. If we can multiply and do some of the addition, we'll see that we have the final temperature of the water, which will be equal to 66.7 degrees Celsius. So now Let's move to the last exercise, which is question number 20. Question number 20 is saying how much energy is required to heat 7.5 kilogram of ice from minus 30 degrees Celsius to steam at 20 degrees Celsius. That means we need to calculate the heat which is required to heat the water or to move the water from minus 30 degrees Celsius to the steam with 200 degrees Celsius. So here we need to pass through different steps. What was given is the heat capacity, specific heat capacity of ice was given, the latent heat of fusion was given, specific heat capacity of the water was given, the latent heat of vaporization was given, and specific heat capacity of water vapor was given. So for this we need to follow the step. We will start by converting the ice with 30 degrees Celsius to ice with 0 degrees Celsius. That's the first step. That means we are increasing the temperature, and that is a sensible heat, which is equal to mc dt, mass times specific heat capacity times change in temperature. Second step is to move to convert water to heat the ice. We heat the ice with 0 degrees Celsius, and we convert it to water with 0 degrees Celsius. That means that there we have the latent heat of fusion, because we are changing the phase from ice to water. That will be the second step. The first one, to convert the ice from minus 30 to ice with 0 degrees Celsius. The second step, ice with 0 degrees Celsius to water with 0 degrees Celsius, the changing phase. The third phase then we will need the heat to convert water at 0 degrees Celsius to water at 100 degrees Celsius. So that also increases the temperature without changing the phase. We will take the mass times the specific heat capacity times the change in temperature. Then we need another step to convert the water at 100 degrees Celsius to the steam at 100 degrees Celsius. That means we are changing the phase. We are changing the liquid, the water to vapors. So there we need the latent heat of evaporization. Then the last step, it will be to convert the steam water with 100 degrees Celsius to vapor, the steam with 200 degrees Celsius. So that is step number 5. So that this will be also increasing the temperature without changing the phase. There we will have also the sensible heat. Then after calculating the heat for each step, then we will add all the heat that we have calculated to obtain the total heat. So now let's start. So we are going to have the Q1, which is the heat required to move the water, to move the ice from minus 30 to 0 ice. So that is equal to Q, which is equal to mass times C dt. Then we have also the second step, the Q2, from 0 degrees Celsius ice to 0 degrees Celsius water. Here we are changing the phase. We are moving from ice to liquid water. So that will be equal, Q will be equal to a mass times the latent heat of fusion. The third step will convert from 0 degrees Celsius, the water from 0 degrees Celsius to 100 degrees Celsius. So we are increasing the temperature without changing the phase. The Q will be equal to mc dt, mass times specific heat capacity times the change in temperature. Then the fourth step, it will be converting water with 100 degrees Celsius to vapors with 100 degrees Celsius. In that case, we are changing the phase. Then we need to use the latent heat of vaporization. So the Q is equal to mass times the latent heat of vaporization. Then the last step is Q, which will remove vapors which has 100 degrees Celsius to water vapors with 100 degrees Celsius. So here we are also increasing the temperature without changing the phase, and we have Q is equal to mass times the specific heat capacity times the change in temperature. Let's then replace the values and calculate the heat. We have the Q1, which is the heat required to change the ice with minus 30 degrees Celsius to water with 0 degrees Celsius. That means the change in temperature will be equal 0 minus 30 then it will be equal 0 plus 30. So that means the change temperature will be 30. So the mass was given 7.5 kilogram times the specific heat capacity of the ice times the change in temperature will obtain 473.85 kilojoule. Then the second step, we will take mass times the latent heat of fusion. Then we get 2,505 kilojoule. Then this step we use the mass times C times dt. The mass, which is 7.5 kilogram times the specific heat capacity of the water. Here we have a joule per kilogram times 100 degrees Celsius. That means we are doing the difference from 100 to 100 minus 0. Then we get 100. We get the kilojoule, which is equal to 3,138 kilojoule. Then the last step we need 7.5 kilogram times the latent heat of vaporization. Then we get this amount of kilojoule. Then the last step we get 7.5 kilogram times the specific capacity of vapors times the change in temperature from 200 minus 100. The change in temperature will be 100. Then we get 1,425.75 kilojoule. Then as the total heat, we will add all the heat and we will get to 26,300 kilojoule.